Thank you, Anita. It's an honor to be here, and thank you everyone for taking out time on Saturday. It's not that easy to take time out on Saturday from busy schedules and do something outside of the schedule. So thank you everyone, and definitely it's a privilege to be here. So as we've already heard, quantum computing is leading the wave now, a next wave of technological innovation. And so we'll briefly talk about that. Uh, Anytime, if you have any questions, you can post on chat with the slide number. I'll try to do pick up questions after a couple of slides, so it doesn't become like, since it's a 2-hour long session, at the end it might be too many questions. So just try to post that with the slide number. So yeah. All right. So here is our agenda. We'll talk about brief history, key concepts, and then we will talk about a couple of quantum properties which are helping us lead the computation and as well as security wave as well. And then we'll discuss about some of the hardware and it's a stack of different layers, how the quantum computers are laid out. And then we'll talk about business applications, like Vanita was already talking about, traffic problems and other simulations. We will talk about that. And a bunch of other use cases which are helpful, which are good for quantum computing. Then we'll discuss briefly about the economics of quantum computing. What are the market looking like in terms of global, in terms of Indian ecosystem, and then we'll dive into cryptography, which is our forte in terms of cybersecurity. How does cryptography is arranged for quantum, and what needs to be done going forward? What are the challenges? What are the solutions? And so on and so forth. And then finally, we'll also look into what are the different challenges quantum computing has, right? If this is such a good thing, why it's not everywhere already? So there are certain challenges which still needs to be evolved, looked into, solved for to go into the next wave. So we'll talk about that. Then there will be certain further reading materials and references using which we have discussed this deck. Let's start with a poll question here. Rajesh, over to you, please.
Okay, 1 second. Can you see this? Vijaya, can you see this?
Vijaya, Rajesh, I'm not able to see.
But I can see a couple of people already started responding.
Okay, fine. So maybe as a panelist, I'm not able to. Participants are able to, I think.
But even the number of participants, it's only...
we are 145, right?
Yeah, but only 10 I could see the...
answer?
Yeah. The team, can you just log into www.mendi.com and use the passcode 8415-1387. 8415-1387. And then can you just participate in the questions, the poll, basically? I can see around 20 people responded so far. It's increased to 30 now. Yeah, it's increasing. And now people can see. Let me rephrase, www.mendi.com and the passcode 8415-1387. 8415-1387. Okay, Aseem, I hope you can see the poll also, correct? Aseem, you are on mute.
I cannot see the poll.
Okay, then what I will do, then I will just share the screen.
Yeah.
Once I say stop, okay?
Sure. Oops.
Okay, and yeah, then we are just closing the poll for one more 30-second more. I can see around 60 people participated. Can you increase to another 10, 15? So that we will get a overall view. Okay, it's around 63. Okay, let me give the answer to Aseem. Aseem, I'm just giving you on chat itself to you.
Sure.
Okay. No, it's not cut and copy. It's not working. Okay. Okay. Then Aseem, I can just read it out somehow.
Sure.
The 20 plus years and 2 people answered. 10 plus years, 14 people. 5 plus years, 20 people. It is already here, approximate 30 people.
Right. So you're right. It's already here. Quantum computing revolution, we are living in one. Let's see how our India is placed already. On 11 March, Ministry of Science and Technology launched a quantum key distribution product, Bangalore-based company QNew. And again on 14th of August, they signed an MOU with Indian Army to go for quantum key distribution product. So Indian Army is going to use quantum computing very soon. They have done the field trials, and now it's ready for commercialization. So India is already powering ahead in this field, and the revolution is upon us. So, all right, so let's look into some of the history of quantum computing. It's a very, quantum computing is really, really old. It is the idea and quantum concepts are very old, from the time of Einstein and a lot of other scientists back in 1900s. And but from a quantum computer point of view, the progress has been largely last 40 years. Initially, physicist Paul Benioff proposed a quantum mechanical model of a computer, that actually Turing machine. So Turing machine, as you might be aware, it's a model which can do computing and create certain, algorithms, right? Or it can solve all the algorithm. It's really a small primitive machine, but it is really, really amazing. So the Paul Benioff proposed that quantum mechanical model for that. 1986, Richard Feynman provided a quantum circuit notation. So this is for gates, quantum gates, etc. And 94 is when it moved into security. So security has been leading the innovation wave here. Peter Shor provided a way to provided a quantum algorithm to find prime integer factors, which had the potential to break RSA encryption. So that's the breakthrough idea in 1994. 96, Love Grover invented quantum database search algorithm, and which was providing a quadrupling of speed up for variety of problems. All problems were not fitting there, but there's a variety of problem which it can solve, right? For in any random brute force search was giving a 4x faster with this algorithm. Coming to 98, Isaac, Chuang, Neil, Mark created the first 2-qubit quantum computer. So that was 1998. It's not too far ago, right? It's for about 20 years. 2019 is when we got into a real world situation where Google claimed quantum supremacy. Quantum supremacy is actually a calculation, or rather an operation, which is done by quantum computers and which will take unrealistic time for classical computer as we know it to take. So it was really a calculation which will take 10,000 years for classical computer to finish, but Google completed in seconds. So that's quantum supremacy. 2020, China performed a calculation which was 100 trillion times faster. 100 trillion, that's I don't know how many zeros are there in that. They performed a calculation in 200 seconds, which would take classical computer 2.5 billion years. So that's the scale we are talking about in quantum computing. Let's look at, yeah.
One request from a couple of people. Some of the people are they believe that the volume is a little low. Is it something? Can you just come a little more closer?
Oh, okay.
Yeah, thank you.
Is it better?
Yes.
All right. Okay, so we will now look at some of the key concepts here. One is qubit. You might hear this multiple times. So qubit is actually primary unit of computing. It is made of either a photon or a silicon. It's an old chip, right? But it's a very special condition. We'll get into that once we get into hardware. But yeah, qubit is the primary unit. Instead of bit, it's qubit. Quantum supremacy we talked about because it's a practical advantage of quantum computing application over the conventional supercomputer. Photonic network. So what really happens is qubit, when we talk about silicon bits, they require very special condition of superconducting coolant, right? It's almost absolute zero, 273 degree, minus 273 degrees Celsius or 0 Kelvin. But however, there is a different way of doing it using photons for that, light photons. So that created network that reduces the overhead, but it's not good for all the use cases. So there are two different options. So photonic network is the network made of quantum computer hardware made of photons. Quantum superposition. Superposition is actually when we have two different states and it is possible to exist in both the cases at the same time. So we have 0 and 1. And I'm sure everybody might have heard this many times. Then in quantum computing, 0 and 1 can be simultaneously. And that is what gives the advantage to quantum computing paradigm over supercomputers that exist today. So we'll discuss that in more detail further. And in the context, you also might have heard about Schrodinger's cat. So we'll talk about that as well. Quantum entanglement is when those qubits are in a relationship with each other that prevents them from acting independently, which means if you have, say, two coins, right, and you flip one coin and it's head, then definitely the other coin is also going to be head. So those two coins cannot be independent. So that's what quantum entanglement is. And these two, superposition and quantum entanglement, are the properties which are being used to derive the advantage. Okay, Schrodinger's cat. So Schrodinger was a physicist in Germany, and he was a contemporary of Einstein. And there was a Copenhagen interpretation was done for quantum mechanics, where people were talking about two states to exist at the same time, right? And then when somebody looks at it, the state changes. So it's like he created a thought experiment. What really you're seeing on the screen is there is a radioactive material which generates a radioactive decay. So it generates those gamma rays, and then there is a yellow one is a monitor which measures the radioactivity, which is called Geiger counter. And that's for detection of radioactivity. And there are certain levers are there with a hammer. And the flask contains a poison. So now this is sealed box, and and there's a cat. They call Schrodinger's cat. The cat is left in the box. Now, from an observer outside, and so the way it works is, right, as time passes, there will be radioactive decay, and from the decay, Geiger counter will be triggered. And with that trigger, it will trigger the hammer, which will break the flask of poison. And cat should be dead at some point in time. So it's a thought experiment, it was not a real experiment. And what he was trying to say is that until somebody sees, they will not know whether the cat is alive or dead, right? Because it's in a sealed box, you cannot see it. But when you see it at that point in time, your the state of cat will be determined whether it is it is dead or alive, right? So from outside, if you are seeing in a sealed box, it's in a quantum superposition state where you cannot determine whether cat is alive or dead. So that's how he explained to his students quantum superposition. It was a very thought he was going to kill a cat for that. But yeah, it has been very famous. If you think about, I mean, if you go and search for quantum, definitely going to get Schrodinger's cat. Now let's talk about bit versus qubits, and again quantum superposition. It's a very small this thing. I mean, it's not a very ominous this thing, right? So if you see a bit, right, it's either 0 or 1. But qubit, so it will either be there in the 0 or 1 state. So think of an electron, it can either spin up or down, so it's 0 or 1. But when the electron in terms of quantum state, it can exist 0 and 1 at the same time, because it is doing in a 3-dimensional model. And anytime the position is determined by a variable. So this alpha and beta variables, which will be some kind of a probabilistic distribution where alpha square plus beta square is equal to 1. So that's pretty much it. So think of it as a 3-dimensional space where an atom electron can be anywhere, and that exact position can be determined. Now this property is leveraged. This property is leveraged for increasing the quantum computing speed and everything. It requires very specialized algorithms to take care of this property, right? So this is how the quantum state is stored in a complex variable. So you can go and select for 1 qubit, you can be storing like, I don't know how many states with alpha beta variables. You can go to infinite probably. However, this needs to be shielded because electromagnetically and cool down has to be almost to 0, because it's very, very sensitive to heat. And as soon as the heat is present or other electromagnetic interference, it's going to change the state. So the data will be lost. So it requires very, very special handling. Let's see if there are any questions. I want to take that up. Something in the chat. No, okay. All right.
Not yet. And what we will do, and we will request every participants to add their question in the Q&A, so that we will pick it up and answer to you.
There is one. Let's see.
No, that I will answer. That's something related to membership. Yeah.
Already.
Yeah.
All right. So let's talk about now quantum entanglement. Quantum entanglement, as I was telling earlier, this Einstein called it a spooky distance a spooky action at a distance, because it does not respect the dimension of space and time. So if you have entangled, say, 2 coins, and you, after entanglement, you just separate them out to another universe, maybe another planet, you can transfer data. That's how powerful this is. So if you think about a standard Alice and Bob in our security world, and they are having one entangled qubit or photon each, and A is flipping the coin and all, so it says 1 0 2 0, exact same will be replicated over there. So you can do a data transfer, and now data transfer is happening without any wires, right? It's not based on wires or anything. So it's not possible for any eavesdropper to detect it or do anything about it. So this will go on, right? So this is super secure. If you want to do say key distribution for your symmetric keys, etc., or any other type of security use cases, Of course, data transfer is really, really slow. It's not going to be in gigabytes, terabytes per second, etc. But data gets transferred. So across space and time without having any hardware or anything else. So that's how powerful quantum entanglement is. Now let's look at where India is. So at 27 January, Department of Space and Physical Research Lab demonstrated this entanglement at a distance of 300 meters. So this was free space between two buildings, and they transferred data from one building to another using quantum entangled photons, right? And the bit rate was 1.8 kilobits per second, was old dial-up connections, which you might remember in our childhood. Or some of us may not even know because this was too old, VSNL connections. And the error rate was less than 10%. So error rate is very important here, because if the error is there, it's very difficult because you don't have any other channel to go over it, right? There are some other technical parameters were also achieved, which were really, really good. So that's where India is. So India is also leading the wave here. Rajesh, can we launch second question here?
Yes, and I launched the question in Mentimeter, and people can go there. 1 second. Yeah, present. Can you see that? And I just go to www.mendi.com and use the code 84151387. Yeah, there are 50 people approximate answer. A team, and we have 193 people. www.mendi.com and use the passcode 84151387. Yeah, there are around 60 people answered. I will wait 30 seconds more. Yeah, around 70 people answered. Yeah, and we have around 195 people now. Yes, we have around 80 answers so far. Team, and another 10 seconds. And please give your answer. Okay, so I'm just now, I got around 80 answer. Another 5 seconds, otherwise I'm closing it. Okay, we have got a good participants now. Let me view the result. Let me view the result. I don't know whether you can see the result, but let me call it out. Aseem, the answer is the way the people responded. Qubit, 18 respondents. QNU Labs, 53. Boson Q4 and Q Labs AI 7.
So what was the question? Sorry, I can't see.
Okay. Which Indian company has signed MOU with Indian Army for quantum computing?
Yeah, QNU is the correct answer, as you rightly guessed. So cool. I'll take this couple of questions which are there. Schrodinger's. So one question is Schrodinger's cat box is like an atom wherein we do not know where and how electron is there, but it is there. Yeah, definitely. So what it is slightly one more level deep, where we are talking about spin of the electron itself, not the full atom. So it has been further broken down into another level where electrons spin is there. So electron is there, but it is not clear whether it is spinning up or down, because it is somewhere in between. So in a three-dimensional space. So that's how we need to visualize it. I hope that answers the question. Next question is, does quantum computing use conventional protocols like TCP/IP? So in an OSI model, what's happening is TCP/IP in the 7-layer model is somewhere in the middle, right? Layer 3, 4. Now, when we are talking about quantum computing, it's very new, and qubit is at a physical layer, and there it's not a obeying right now 7-layer model right now. It has its own error correction and all those fault tolerant type of situations. So we will get into that when we see the stack. And that also takes us to one of the challenges in quantum computing, that there's no standardization yet. The technology is evolving, and bunch of competing technologies are working in the field. Whoever wins will define the standards. So right now, to best of my knowledge, there are no standards, and that is a good thing actually, because it will not affect the innovation or slow it down. So I hope that answers the question. Let's move to the next thing, right? When you hear about quantum entanglement, then first thing which came to my mind was, how do you create quantum entanglement, right? At the first place. So what really happens, it's really simple process. And BBO is some kind of a chemical crystal, and the light is thrown on that. It's a violet laser. They sent it to this BBO crystal, and that produces a small number of pairs of near infrared photons. So think of it, they create a photon, right? And whatever photon you sent in, it gets split into two because of conservation of momentum. Now, and because of this property, they are having certain properties in common. And when they are split, one is horizontally polarized and another is vertically polarized. So now you can put the right detectors in place. The second box is actually a detector, and using which, if you put the detector in a horizontal way, you can detect it. Horizontal, of course, if you put a vertical detector, it's not going to detect it because it's horizontally polarized. So that's how you kind of split the two atoms, right, which are entangled. Now, entangled are the properties. Their properties are entangled. So once you pass through these detectors, and then you can further take it along by putting certain tubes. So these entangled photons can now be separated via certain tubes. It will travel in that, and then you can do whatever with it, right? You can take them apart as long as that your tube and physical limitations allow. You can go all the way to 300 kilometers or however, right? Or if there is another way of taking it to Mars, you could take it to Mars. So that's how they are kind of stuck together. Now there is a second way of also generating against concentric circles. So there are two different ways of generating, and it uses the BBO crystal. What about Moore's law, right? We have been reading about Moore's law forever. What happens to it when we move into quantum world, right? What Moore's law is, processing power doubles about every 2 years, right? Which is a power of 2 to the power 1, 2 to the power 2, 3, 4, and so on, right? And if we look at the hardware which is backing Moore's law, our computer chips are going smaller and smaller. Now classical computer chips are at about 10 nanometer, right? That's the size of the chip we have. Most of our chips are slightly behind 13 to 17 nanometers. Think of it like a 2G, 3G, 4G, where 4G has come, but not everybody is on 4G yet, or 5G is rolling out, but 4G is still working. So that kind of situation. Now, when you make the chip even smaller, at around 7 nanometers. That's when classical physics starts to break down and quantum mechanics start to take hold. So that's your kind of limit of physical, how deep you can go, how small you can go according to Moore's laws, because that hits the physical boundaries of the world. Now, so there's a gentleman named Nevin, and he has proposed another law calling doubly exponential. So it's actually 2 to the power 2 to the power 1. So those the variable is at another level. So that's how Naveen has proposed. Now the beauty of it is nobody can test it. It will still take a long time to figure it out whether he was right or wrong. Whether it is 2 to the power 2 to the power 1 or whether it is 2 to the power 4 to the power 1, we don't know. But it is something which he has proposed. So we'll watch out for that. So yeah, in short, Moore's law is not irrelevant. It has become supercharged in terms of quantum computing. So when we think about quantum computer and classical computer, what's the difference? So one of the main difference is quantum computing uses qubits, which can represent 0 and 1 at the same time, as we were talking about, which is bound by certain probabilistic variables, alpha square plus beta square is equal to 1. So that's your quantum computer, whereas classical computer is still on 0 and 1. So that's the main this thing, right? And when you talk about power increases, right? The exponential power, that's what we were talking about, Nevin's law and all, right? As soon as you increase the number of qubits, the power will increase exponentially. That's your processing power. However, classical computer is still sort of linear. It is not that exponential. It has relationship with resistor transistors on the chip. So that's how this quantum computers are going to. There will be an inflection point, and after that, it will just fly away. Probably some other law will physical law will limit its kind of computing power, I guess. We'll watch out. I'll be interested. Now, when we come to error rate, quantum computers have very high error rates. Because of thermal interference, the electromagnetic interference, it needs to be really sealed, ultra cold, and these kind of, they require really special handling. And to leverage that superposition state of something between 0 and 1 require really specialized algorithms. Whereas classical computers have low error rates and they operate at normal room temperature. So that's the another main difference here. Now, when we come to task, we're talking about certain situations, like if you want to do word processing, etc. A quantum computer is not the place to be, because quantum computers are too specialized for now, and this is best suited by our average PC and laptops. However, when we are talking about huge data optimization algorithms, simulations, like we heard in the traffic problems, those kind of things, quantum computers are the way to go. So those are the problems which should be solved by quantum computing. So we'll see how that goes. Let's see if there are any questions here. Okay, no questions. All right, we'll keep moving. Now that's our logical stack. So it's still not a hardware stack. We'll get there on how that goes in the next slide. However, this is a logical stack proposed by Microsoft. It is breaking down at certain level. If we look at qubits, right, that will be at the bottom. So that's your semiconductors, superconductors, and dielectrics, right? That's your topological qubits. And then there is a gates and wiring, etc., which are done. And cryogenic control is the temperature control, which is maintained around absolute 0. So that's your cryogenic control. And in between, so what they have done is they have created a chip called Gooseberry. And that is what they are doing is that think of it as a kind of an interface between a quantum plane and classical plane, right? So that's your quantum classical interface, where this chip called Gooseberry works in both the worlds. So they somehow manage that, right? And that's what it's actually is taking the instructions from your classical computer, and where additional solutions, software applications, etc. are deployed. It could be cloud, it could be whatever else, right? And that's how you interact with a quantum computer. Uh, so that's how the stacks are laid out. Qubit, cryogenic controls, this chip in between which does kind of interfacing, and then you have your standard solutions, softwares, application, all this layer 7 things we were talking about. Okay, there are two questions. Limitation of quantum computing. We don't know yet. We are still at a place where we are we kind of exploring what humans are is still exploring where it will go. We have not even crossed. Once we get into cryptography, we'll see where we are, how much time do we have, and how many bits we are at. Where that takes us, we don't know yet. So we'll take probably a couple of decades to figure that out. Second question is, how good is D-Wave? Yeah, D-Wave is really a good company. How good, I cannot tell. I don't know. They're using a different mechanism for quantum annealing, which is quantum gate. So they have a completely different model than Google or Microsoft are pursuing. And D-Wave also has a tie-up with another cloud company. So I will see that as well. So yeah, really good. So they are commercial and all that. They have a cloud interface as well. So definitely they must be good. Yeah. All right. So this is as close as we will come to OSI interface for now. So if we look at the top user interface, that's called QAAS, Quantum Computing as a Service. So that's your user interface, and those other user interactions like cloud service, etc. will sit. Now, if we go a layer below, there will be quantum algorithm and applications which are especially coded using developer tools. So think of it as a kind of a SDK type model here, which is quantum algorithm and quantum applications here. That still is providing very high level of abstraction here, but in a quantum world. So you still need a separate quantum SDK, etc. To interact with it. And then today's classical interface will be at a QAS level. Now, once we come down further, there are algorithms which are compiled into, so these algorithms are still at a very high level abstraction. If you come below, there are circuits, quantum circuits, gates, etc., etc. So that they need to have some kind of a compilation here for quantum error correction, and those kind of things. These are software errors. They are still not hardware errors. Algorithmic software errors, etc., error corrections. So these are those layers. So these are dedicated layer for error, because errors are really I mean, there are too many errors right now. Going forward, they may probably resolve it and move to a newer technologies, etc. Maybe better physical materials. We'll see, right? And now then we are talking about physical connectivity between devices and other hardware, right? So this is a hardware-aware compiler, where think of it like a device driver, right? Which will interact with a lower level of this thing, right? Your hardware. After that, we are talking about, this is your quantum firmware, right? This is this dotted quantum firmware hardware error mitigation. That's where hardware errors are managed in terms of heat, in terms of other interference, those kind of things. So it's at a hardware error level, and below that is a physical qubit hardware. So what really happens is, if you have too many qubits, there are physical qubits, and then as you move on top, there will be logical qubits. So there is a reduction in that because of errors. So you have 10,000 physical qubits. You're probably logical qubit may not be that much because of errors, etc. So it's the other way around. In our classical computers, you have one VM, you virtualize it, you make 4 VMs out of it. But here we are not there yet, where we can virtualize qubit itself. Some point I'm sure they will do it. Okay, they have a couple of questions. Share more on quantum as a service available today. All right. Yeah. So there are a couple of reading links we will have at the end of this session. There's a slide, so you can follow that. Supercomputer plus quantum computing. What will be the impact? Yes, impact. We are coming to that. So this we'll discuss in the next few slides. Okay. Question is, there is a general opinion that qubits are extremely fragile. What is your take on this? And if correct, how do you see the future? Also, your thought on efficiency and heating issues that are related to quantum CPU. Absolutely correct. They are extremely fragile. As soon as you try to measure it, they will spin up or down. So all this alpha, beta, whatever the power comes from, it will go away. So those kind of things are there. And they're also very, very fragile in terms of heat and other error correction. So that's why it is not everywhere yet, because it's extremely fragile and requires a special handling in terms of isolation of magnetic, electromagnetic interference, as well as your temperature control. So, but we'll get there. So the way my gut feel is, of course, I don't know. My gut feel is that it will be our interaction with quantum computers are going to be via cloud. They will run in some specialized data center. They will, let's go back to this hardware. I mean, this stack, right? So this, if we see this quantum firmware, quantum aware, quantum compiler, etc., those things will run in, say, I don't know, Amazon or Google data center somewhere, powered by either D-Wave or anybody else, or Google, in fact, has his own, IBM has his own this thing. So they might power it on their own. And then you will have different level of abstraction. There will be certain access which will be given for if you want to develop an compilation and algorithm, etc. You will get probably third layer access from the top, right? Second and third layer. But if you are a say application programmer or a user, you're gonna get probably a further level of access from the top user interface, QAS. So I think that's how it's going to pan out. We will not require a quantum computer sitting in our basement or in our apartments. So that's that, I guess, is there today. We don't know whether it will go PC way, where everybody will be having a super quantum computer in their pockets in, say, 50 years from today. There's one more question: is quantum computing is used for storage reference electronic spin like microprocessor does? Can we divide these? We have storage and microprocessor. So it's generally used for processing large data right now, not as much as for long-term storage like Glacier or S3 buckets, etc. Right? So they are not like your RAID hard disk, etc. So as of now, and it's mostly using it for algorithmic supremacy. Now coming to industry applications, let's take an example before we dive into that. So there are about 30 million electric vehicle target in 2 years for India. Now, one of the problem statement there is the biggest problem for electric vehicle is the charging station, right? There are a bunch of options. You have petrol pumps, you have malls, metro stations. Where do you build charging stations for being most efficient? It's a very, very big multi-dimensional, multi-variant problem. So there are too many combinations here. There's a company called Artificial Brain Tech. They have been on this problem. And if we want to see the scale of quantum computing power, it is 8.5 into 10 to the power 15 combination quantum computer can process in 3 seconds. That's the power, 8.5 into 10 to the power 15. So that's beyond trillion combinations, right, in 3 seconds. That supercomputer is going to take a long time to do that. So this is the one of the applications which is already under process by artificial brain tech company. Then there is another one for wind and solar farm locations. Right? There are too many variables. There is a nature where the sunlight, day of the week, right, and the seasons, slope of topography, etc., etc. Too many variables there. Rainy season, etc. Over the period of year, how to optimize the sunlight and wind, multiple variables. So that's a big problem, and supercomputer is, I mean, quantum computer is for the rescue here. Now coming to healthcare, right? Industry specific applications, drug discovery, because there are too many variables again on that, and drug discovery molecules. Now there's something called protein folding. Finally, what happens really is that when you have DNA, RNA, and then finally that gets encoded into protein. We have all heard about RNA vaccines lately. From RNA, it really goes into protein, and that how the protein will fold. They call it folding, which is how the protein will turn up in the body and how it will react to rest of the system in the body, right? So that's unpredictable. There's really too many combinations there. So that's where quantum computing is going to help to create a computational model of that and generate candidates for protein-based drugs are very, very fast, because you can reject a certain combination right away based on toxicity or whatever else they already know about. Genomic analysis is another candidate. Finance risk optimization, when we are talking about risk, there's too many variables out there. Things like a general stock market in number of variables, infinite variables. So how do you solve that? You can solve that using quantum computing. And that's where this, if you think about, right, quantum computing as a service will come into play. Financial companies like Goldman Sachs might have certain scientists deployed to generate certain algorithms at that layer, interacting with cloud service. And then you have users who are building certain kind of UX-driven applications on top of that, which will take user inputs and generate certain outputs using the algorithm and the quantum computing in between. I mean, at the bottom layer. So fraud detection, Monte Carlo simulations have seen 4x improvement in terms of financial risk assessment. Now coming to cybersecurity, cryptography, random number, key distribution, secure VPN, secure messaging. There are a number of things at different layers. We'll look into different layers of applications there when we get into the cryptography section. Now here is looking into economic value add. I think we need to go slightly faster. We are on time. Okay, cool. 2035, this is McKinsey report, and they are talking about 700 billion value in terms of economic value add on upper estimate by 2035, and lower estimate is about $300 billion, right? Which sector will pick that up is also broken down. So chemicals, pharmaceuticals, if you see, the gap is wide between lower and upper estimates, huge. There's no overlap, which means it will either go exponential or it will be a dud, depending on how drug discovery pans out. Similarly, automotive and financial services. Financial services are like way out there on that. So that's the impact of in terms of economics. Coming to India. This is situation. This is from a NASDAQ report, which was released last month, I guess. What will be the value at 2022 is 0. 2030, we're talking about 310 billion. So almost half of global value, which McKinsey has predicted 700 billion, 300 will be in India. That's an amazing prediction. I hope that's true and it comes to pass. It will be really exciting for all of us and people who are coming live on the workforce to see this kind of $310 billion of economy just coming from quantum computing. So We'll see. Now, development of indigenous quantum computer. We are really at 3-4 physical qubits. Now we are going to go to 10,000 plus logical qubit. That's the goal. Number of startups who are just 14 right now will go to 400 to 500. Enterprise adoption rate will be almost half by 2030. That's a tall order. It's a huge jump. So which means we are already on the treadmill. We have to run faster to catch up. And then last but not the least is workforce. Where are the people? Right. So we have less than 200 people right now who are quantum literate, rather are ready for work in quantum fields. And target is about 30,000. The beauty of quantum is that there are multiple types of people required. Some people to handle hardware, cooling, etc., algorithms at all level people are required. This is going to explode in terms of opportunities going forward. That's what I personally believe. Now, similar breakdown, if we look at economic value add here, this is how agriculture, financial services, healthcare, heavy industries, etc., high tech are going to pan out. There's a lot of numbers here. But yeah, I mean, quantum computing is 157. And then communications, materials, sensing, etc., are also adding up by the vector. So it's a very good matrix. And we can see by quantum computing how much it will be for quantum communication and materials and sensing. So or by industry. Let me take a couple of questions here. First question is about quantum computing and decryption. We will get there when we get to quantum computing and cryptography. Next is dollar and timeline. We have a slide for that. Slide 17. As per most examples on slide 17, do we reckon that QC is for big R&D rather than purely business commercial use, at least for next? Not really. Actually, you can go to certain cloud platforms and use the quantum right now as we speak. Swipe your card and use it. So it's not for big R&D. It's already virtualized. It is powered by D-Wave systems. And there is a cloud interface as well. I think we have a quiz question. That's why I'm not revealing the name. So we'll get there. More thoughts on needed skill sets. Yeah, so I mean, skill sets, it will be at all level, right? If you go back to the slide where we were talking about, let's see, we'll go back to this slide. So we are seeing at each layer the skills are required. Somebody is going to make physical qubit hardware, right? There's a lot of things required over there. Somebody has to do error mitigation algorithms and hardware protection and etc. Every box is an opportunity here, right? Quantum compilers, who is making that? There are opportunities there. Quantum error connection. There are compilation SDKs. A lot of things are required. And then coming to quantum as a service, cloud, there is going to be user algorithms as well. So opportunities are everywhere. Just need to start somewhere based on our interest and inclination. Now, with that, we'll launch poll question 3.
Okay. I request everyone to go to the mendy.com and use the passcode 8415-1387. I'm just enabling the question. Yes, I enabled. The question is, some cryptographic algorithm are secure against quantum challenge for now. How long are they expected to remain secure? I can see and approximate 20 people answered so far. And I request everyone, and we have 210 plus people. Yeah, it's www.mendy.com and the use code is 8415-1387. Okay, and I could see around 40. 30 seconds more. Yeah, 20 seconds more. I could see around 70 people answered. Yeah, 10 seconds more. I could see approximately 80 people answered. Okay, 5 seconds more. 5, 4, 3, 2, and 1. It's around 80 people answered. Aseem, and the answers cannot be predicted, and that's a maximum with 45 answers. 20 years, 5, and 10 years, 7, and less than 5 years, it's 20. Cannot be predicted, it's reached to 50.
Yeah, so actually the correct answer is roughly 20 years. And once we get into cryptography section, we'll see that on the algorithm side. So yeah, I guess the small number wins this time.
Okay.
All right. Let's look at what is the scene in terms of which companies are working on this, right? Global pioneers. Google is launching 1 million qubits by 2030. That's the scale they're talking about. IBM is launching 4,000 qubits by 2025. So Google is probably light years ahead in terms of progress here. D-Wave is launching 7,000 qubits by 2025. So they are ahead of IBM, but slightly behind, rather large number behind. Or maybe there is a curve in between 25 to 30, they will catch up. Amazon is providing cloud-based access to quantum computing powered by D-Wave. It is called Amazon Bracket. You can go to Amazon and subscribe to the service right away. And as usual, they give 1 year free for certain free tier, they have it. So you can go and play around. I don't know what it does, what all can be done with it, but yeah, of course, feel free to play with it. Microsoft is proposing a hardware stack and things like that. So Microsoft is also in the game. Coming to Indian situation here, this is a busy slide here, but let's see, there is a government agencies who are working on it, things like ISRO, CDOT, right, and Science and Technology Department. These are the government company agencies who are working on it. And then we have startups. So there are 2 startups which I've highlighted, QNU and QPI. Any guesses? You can put on Q&A if why they are highlighted. Any guesses? 10 seconds. Just any guess? Okay. So they have a commercial product which can be used. The rest of the companies are in kind of R&D phase, but they are their product is commercially available. Then there are certain service providers. There are already all the Indian service providers are there. Infosys, Capgemini, Tech Mahindra, TCS, HCL, all the usual suspects are here. So I'm sure they are training people and bringing people online in terms of workforce there. Academic side, IITs, right, and other institutions are on top of it. So there is a research, IIT Delhi, IIT Madras, Calcutta, and other universities, etc., are working on it. All right, so now let's come to cryptography. Let's do a quick recap here. If you see our encryption systems, there are 2 types of systems, like asymmetric and symmetric. Asymmetric, RSA, DH, and others. Symmetric, block and stream ciphers, and they are further broken down into other algorithms. Now, if we see their characteristic, the key usage for symmetric algorithm encryption, same key for encryption, decryption, both. That's why it's called symmetric. And for asymmetric, there's a different key used for encryption, decryption. Speed is very fast for symmetric encryption because the same key is used. And asymmetric encryption is slow. Key length, if we look at symmetric key encryption, 128 bits are enough in terms of NIST recommendation. But asymmetric encryption really requires large keys, which is 2048 bits. If you look at symmetric key, both the keys, the knowledge of key has to be with both the parties, proverbial Alice and Bob. But in asymmetric key, only one party knows both the keys because they hold the private key and public key is distributed for purposes, right? So though both the parties do not know both the keys. Usage, if we see symmetric key is used for data confidentiality, but asymmetric key can be used for more than that, can be used for non-repudiation and data integrity as well. Symmetric key advantage is higher operating speed because it is super fast. However, asymmetric key is more secure because it is long and it takes long time to do it. And that becomes a disadvantage. So the advantage is really a disadvantage because it is more secure. You pay the price in terms of processing overhead. Symmetric key is disadvantages. How do you manage the key? How do you distribute the key, etc. So these are the problems here. Now let's look at quantum cryptography and post-quantum cryptography. You might have heard these two terms. Quantum cryptography is actually using the principles of quantum mechanics to send secure messages. And it does not rely on mathematical encryption. So it is truly unhackable. However, post-quantum cryptography is actually misnomer. It refers to cryptography algorithm, usually our PKIs, that are thought to be secure against attack by a quantum computer. So that's post-quantum cryptography is. Okay, there are no questions here. Let's move forward on what is the quantum challenge to cryptography. Now, our classical cryptography is actually a computational security. The fact that we rely on aspect that it cannot be computed, the key cannot be determined in the time which is commercially viable, right? You can, of course, you put classical cryptography and its challenge. Now, coming to quantum cryptography, it's extremely efficient for large computation, and it solves the quantum key distribution problem. We'll see in a minute in the next couple of slides. And this also has a very unique advantage built in, which is error detection. So quantum theory has a property that if some measure certain physical qualities, because they are complementary, if you measure it, it will change. So if you are sending from Alice to Bob and Bob measures it, it will change. But it is measured only once, so they know, both the parties know. But some eavesdropper does it, it will change in between. And when the Bob receives it, it will already be changed. So they will detect it, that it has been changed. So you can drop the key and start all over again. So it has a built-in eavesdropping protection into that. And quantum entanglement we already talked about. Now let's look at second slide on quantum challenge to cryptography. So these are certain cryptographic algorithms, and RSA, ECDSA, DSA, etc. are no longer secure. Now, AES, SHA 2, 3 are secure for now. And that's where they are secure now for almost 20 years. Expected lifetime is slightly less than 20 years. But if there is a major breakthrough which is unanticipated, it could be less. So that's where things are. And they are expected to be breached when it reaches 3 to 7,000 logical qubits. So that's where they're supposed to be breached. Actually, question 4 is already done. Let's move to the next slide. How much time? I think somebody asked a question, right? How much time do you have?
There was one question which was related to, 1 second, let me post that as well. Let me read the question. 1 second. The question was related to, 1 second. Which company in 2019 claimed to have reached quantum supremacy by performing a series of operations in 200 seconds that would take a supercomputer? Do you want to present that?
Sure.
Yeah, okay. Let me present it. Okay. Hi, everyone. And please use Mendy.com. And the passcode is 8415-1387. I can see around 20 answers so far. I will keep it for 1 minute. It's already 20-second over. And let me read it. Which company in 2019 claimed to have reached quantum supremacy by performing a series of operations in 200 seconds that would take a supercomputer? Okay, so we have around 70 answers. I will keep it for 25 seconds more, and the timer is going on. Okay, around 70. And www.mendy.com and 8415-1387. I could see approximate 80 numbers. Let me put the reverse number 10 second. 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And we have 80 responses so far. And most of the people choose Google, the Facebook, that is Meta 8, IBM 14, Microsoft 4. The remaining people choose Google. Aseem.
Yes, Google is the correct answer.
Okay, that means most of the people answered correctly.
Yes.
Okay, thank you. Then you can continue. Around 80 people answered.
All right. We are seeing a very good participation in quizzes, polls.
Yes.
All right. So we were talking about how much time do we have. Right? So that's our qubit timeline estimates by Gartner. So if you see on the left-hand side are millions of physical qubits, which translate into less number of qubits. And the reason is decoherence error. So these are the errors. I mean, I think they have a scientific term for it. But that's the errors which bring the logical qubits down, which can be actually used for computation, etc. So post-quantum cryptography, we're already there. And in between 300 to 500 logical qubits, and meaningful quantum advantage were beyond 23, and QML to AI. So those are things like 2028. Financial services will gonna catch up in between, somewhere between 23 and 28. And then all historical RSA encryption can be cracked. It's somewhere after about 2038, something like that. So that's where they're talking about. All superpowers have copied a lot of encrypted data in anticipation of arrival of quantum computing. So China has copied massive amount of data. US, Russia, all have been copying. data. They just store it. They don't know what it is, but they are storing. And when quantum computing reaches that level where RSA is broken entirely, they'll run that data on top of it, and they will decrypt and figure out how adversaries think. That is strategic advantage they're looking at. And US and Russia have been doing it for decades now. You copying older data, and when the computing power increases, they decrypt the older data and figure out what their adversaries were thinking, or even allies. They don't worry about allies as well. So yeah, that's how it is. Now when we are talking about cryptography, right? Before we get into cryptography stack, we have to talk about random number, because random number is at the base of all the cryptography. So what is the problem, right? Why do we need random generators? Because it may lack of randomness will lead to pattern detection by hackers, which will be exploited. So that's why the better the random number is, the better the encryption and the rest of the algorithms are going to be. We use random numbers in our everyday life: bank OTPs, lotteries, CAPTCHA, cryptography, statistical sampling. In medical fields, for every drug, there is a double-blind randomized controlled trial. So if that's not random, the drug may not be as effective as thought to be. So those are the some of the things where random numbers are required. Now, there are two types of random number generators. One is P random generators, which is pseudo, right? And T are true. So pseudo random number generators are really determined on deterministic algorithm, which convert actually some kind of input string into a large string that satisfies some NIST standard. So that's your pseudo random number generator. It produces fast, but they're not truly random. If algorithm and initial input string is known, then all the random numbers can be predicted. That's PRNG, but it's extremely fast. And for all commercial low value purposes, it might satisfy. Now coming to true random number generator, you're talking about CTRNG, which is your classical classical random number generator. And then second is quantum. So true random number generator is of two types: quantum and classical. In classical, they depend on thermal noise or a cosmic noise, etc. The problem with them is that although they appear true random numbers, but since they are still built on some kind of physical process which cannot be modeled today, but that does, like what type of noise it is, or say atmospheric noise or thermal noise, we are considering it random because we are not able to model it today. But if it gets modeled tomorrow, they will not be random. They will be deterministic, and people will be able to figure it out. That's one problem which it has. Second is, it's very difficult to ascertain the quality because it's random and we are not able to monitor. We don't know whether this random number is good or bad. We don't know that. So that's the problem with classical true random numbers. Coming to quantum, there are two types of, again, optical and non-optical. Non-optical depend on atomic noise, electronic noise, etc. However, optical depends on qubit and macroscopic. So qubit is what we'll talk about. Since quantum mechanics is inherently non-deterministic by theory itself, it's a very good source of true random numbers. A lot of questions. Let me see. I can just. The workforce you mentioned on slide 20 is still there is a lag in cybersecurity professionals, and the dynamics of CS arena continuously changing. A lag is widening. On similar lines, realistically speaking, for the QC arena, think the need would be addressed as mentioned, or will there be another big race between demand and supply? It will depend how the demand is shaping up. If And of course, there is a lag, always lag in human resources development. Because it's from the demand to translate into money, to translate into incentive going forward, all the way to the colleges and the facilities getting built and the course books and et cetera, getting launched. It takes time. It takes on a scale of decades. However, market today demand really moves on a scale of probably quantum speeds. So I guess if I have to hazard a guess, I would say demand will certainly outstrip the supply. If we look at Google target in 2025, 2030, we're talking about 2-3 years from today, right? And Amazon bracket is already there, so you could use it. So I would say demand will certainly outstrip the supply. So it will be a good way, good field to be in. That's my guess. Of course, there are a lot of uncertainties. It's not a slam dunk. So still risk needs to be watched out for and managed, because there have been several good technologies like 3D printing, etc., which are there, but they did not pan out yet in terms of expectations. So we'll find out. Emerging threat. Okay. Audit systems and apps. So I think this is just a comment. Emerging tech, so very interesting. We have to see how the audit and systems, apps, etc., are keeping up in coming days. One more question is, what areas of education would you propose to be focused at university level for students? I think there are a couple of courses. I saw something in Pune, which is already doing some kind of a master's level engineering there. Professional education certifications. I think this is upon the generation to make that happen. People on this call are supposed to create those education and certification materials and bring them online. So I would say we are the pioneers. We need to get into the field, define what the need should be, and then bring everybody else online. That's how I would say encourage everybody and motivate everybody. We should be the lead, we should be the torch bearers here. Instead of waiting for others to define the certification, education, etc., we should go there, do that, and define the needs, get it done. Okay, so we have seen the hierarchy here. So we'll talk about true random number generator, optical, and qubit here. How do we do that? So there is a light source, and a single photon falls on a balanced beam splitter. What does that mean? Is that there is a balanced beam splitter is it will split either two ways, right, left or right. So that's truly random based on quantum mechanics, mechanical properties, and you can encode that as 0 and 1. Left is 0 and right is 1, and then when you assemble that 0 and 1, you have a random bit sequence. So those are truly random sequences. Now, one of the use cases on the cloud could be that this hardware is somewhere in between, in the cloud. You use it as a service, you give a command here and say, give me a random number between whatever, right? It will trigger the light bulb, it will generate that stream and then give you random numbers. So that's probably one way a cloud service can interact and give you a quantum number that can be utilized anywhere else. So that's just one use case I'm imagining. How does the quantum key distribution work here, right? So there is Alice and Bob, and so you have two ends. And there's a photon source. So Alice is sending the key to Bob, right? Now it sends the light particles via polarizer. Polarizer will work either horizontal, vertical, 45-degree left or 45-degree right. So that's your diagonal polarizers, which is 45-degree left or right, horizontal, vertical, that. And now you can encode with an understanding with Bob that if it is left, polarized 45-degree, it is 0, and horizontal is 0, and right so you also need an out-of-band channel to kind of convey certain information, right? And right 45-degree is a polarizer. You take it as 1, vertical you take at 1, right? So that's how when you send it, your information gets sent now. And then what's going to happen is the photon will go to the receiver, right? And on the receiver side, you will have, again, detectors, which will have, again, beam splitters, right? Horizontal, vertical, or diagonal. And if the wrong splitter is used, it will drop the photon, right? Because it cannot pass through. So that's how this will work. Now, Bob needs to know the sequence of photon and the polarization angle with which Alice has sent it in order for the key to be transferred. So if the photon number 1 was sent with a diagonal polarizer, Bob needs to know that sequence 1 photon is a diagonally polarized. So that information is there. And with that information, it's able to put the right sequence and detect the right key. Now, if you see in between, there is a hacker which is tapping into that photon transfer. What's going to happen with that is it will change the property. And as soon as the property is changed, the sequence is not going to match because it will change its polarization. The property changes by using quantum mechanics properties. So now Bob's sequence will not match. As soon as the sequence doesn't match, Bob knows the key is compromised. So they will start all over again. So that's how quantum key distribution works. Okay, so now we will talk about reference quantum cryptography stack. This is source credit is QNU. So at the bottom, we are talking about quantum random number generator. So they have certain one platform can have a quantum random number generator, and the random number itself can be used for IoTs, for network seeding, authentication, secure OTP, etc., etc. Right. So that's your base use case for random number itself. Now it goes to a further level where you can have quantum key distribution, what we just talked about. So you have a key server and secure link, etc., and you can do a quantum key distribution. That is again built on top of your quantum random number, right? So you generate random number and then feed through that earlier slide, and then that's how you get to that. Now, next application is key vault. So once you are having the key distribution, you can have a key vault and do the key management. So these are like application level usage. The random number, then key distribution. As soon as you are doing key distribution, you need the key vault as well. And then it comes to their application level usage, which is PQC, post quantum cryptography. So these are your application level data security, cloud security, MFAs, etc., etc. So these are application level stack which are using quantum keys for encryption. So that's how using key vault. So that's the reference stack. So it becomes kind of a hybrid quantum key. You don't have to change everything what we have been doing so far, but it will be used using true quantum random numbers and quantum key distribution. So it is really, really secure. It cannot be hacked into. So that's our reference. Let's see, some more questions are there. Let me see if I can take that. How to start with the quantum computing and security perspective, where to get the training from. So there are certain further reading links are there, which is there in the deck. I'll just come to that. And there are many other things. There are courses from IISc, MIT, which can be taken. So yeah, those are the things which we can look into. Next question is, do we need to infuse more academic talent in our academia from outside India for teaching quantum computing? Yeah, I mean, base level physical, this thing is done in right now with government institutions, ISRO and those other things which are creating base level qubits, etc. Applications, etc. level is being created. So yeah, so that's where we are. How in terms of academic, it is from outside India, I am not sure whether those kind of facilities are available and they will be truly excited to come to India and continue their research, given the facilities, etc. Might be better in foreign geographies than in India, but I truly don't know. So it's kind of difficult to guess at this point in time. All right. Last question right now is, powerful tools developed in intelligence and military context tend to find their way into hands of law enforcement agencies, even at local level, often without political oversight. How can policymakers prepare intelligence, military, law enforcement to contemplate the implication of quantum technology? It's a mouthful of question. Yes, it's a very right one at that. I would say we are still figuring out the data privacy and we have not come to a conclusion there. So quantum might be a far cry right now. So let's be hopeful. But I guess it's quite far off from policymakers, if you ask me. One more question. So the quantum computing cloud will take data using cloud interface and solve issue problem data analysis. Yeah. That's how it's going to be. So some kind of interface, and because cloud is already a delivery mechanism, which is tried and tested. So yeah, that's how it's going to pan out. All right. We were talking about the challenges. If everything is so good, what is the issue here? Right? Why are we not seeing quantum computing everywhere? So interference, as I was talking about, leads to errors, and that requires fault-tolerant system, which is some time away. So yeah, that interference, then engineering, it's really an engineering problem, if you see. Keeping something in quantum state long enough to use it, that's where the problem is. That's where actually rubber meets the road. Because it needs to be in superposition state long enough for data to be sent in, encoded into that state, and then algorithm should harness that power. So that's where it is. Temperature control, cryo cooling, that's absolute zero. That's a lot of energy. Investment is quite poor, except China is leaping ahead on $15 billion. Everybody else is far behind. US, UK, India is just 1 billion each. So that's that. Talent, again, talent is really sparse right now. So there is something called NMQTA, which is National Mission on Quantum Tech and App. That's government initiative, NMQTA. You can look that up. It has a target to create a workforce of 25,000 people in 5 to 7 years. They have proposed a $1 billion investment. However, they have not gotten clearance yet. So it may still be on the paper yet, but yeah, that should get cleared maybe. DIAT Pune and IISc, they have an MTech course. So that's can be used. Q Labs is also offering 6 months internship. So that can be looked at. Now coming to ecosystems, right? R&D, design, engineering, simulation, testing. There's a lot of things are required in that space in order to get to a realistic target here. So there's a company called Innogress. They are setting up a tech park to host R&D, design, engineering, simulation, etc., under the same roof. And they're talking about 300 million initial capex. So that's a huge ask, but let's see if that gets um, come to fruition. Talking about what should leaders do to prepare for quantum future, right? Need to follow the industry developments, because there are actively you have to screen for quantum computing use cases with in-house teams maybe, right, or collaboration, joining some kind of consortiums. So these are the things the industry needs to be developed, development needs to be followed very, very diligently. There will be risks, as I was talking about. It's not slam dunk. There are many technologies which have fizzled out before going to masses. This is unlikely to be the case because for quantum, because there's been more than 40 years in the making. But still, we still need to watch out for most significant risks and disruptions, opportunities in our industries in order to take the full benefit. Then we also need to figure out whether to partner or invest, right? Software companies or facility access, knowledge, talent, etc. So how that strategy needs to play out. Leaders needs to recruit at least some quantum computing talent in-house, so they can team up with others and find out, explore possible use cases, etc. Screen strategic investments in quantum computing. Those are the things. So these are the places where we should be as leaders today. We need to be in those fields, right? Guiding organizations what to do forward with that. And last but not the least, prepare for building quantum-ready digital infrastructure for basic operating demands, right? Make up relevant data available in digital databases, because there will be digital data needs to be fed into quantum. So that's required. So those are the things needs to be set up. There will be conventional computer workflows needs to be quantum ready, and so on and so forth. So these are some of the things which can be done. Now the last question of poll. Rajesh.
I think Rajesh is not there. So
okay.
Can we go on with that?
Yeah, we can go on. All right. Yeah, these are the further reading. There are some books, influencers, online course in collaboration with ISC, quantum computing and security course by MIT. There's a free online lab by IBM, blogs, newsletters, certain white papers. So these are some of the resources which we can use to keep the torch burning and move forward. And these are some of the references which are used for this. Thank you very much. I'll post the slides on my LinkedIn, so you can all get there. If there are any more questions, we can certainly look at that. I see there are 2 questions. Okay, so one I've already answered, PPT deck. Yes, I'll post that in LinkedIn so you can download it. Okay, one last question is, so corporates will not have quantum infra and they will use Google, IBM, etc. Yeah, I mean, that's how I think, because it's very costly right now to host this infra, etc. So I don't see that happening. If Google, etc., are already building general purpose computers in terms of quantum, that should be leveraged by everybody. And we have already moved away to cloud. People are not hosting their own data centers anymore, right? Most of it. So we will certainly take advantage of that similar paradigm, and it will go centralized. I don't see that every company, unless there is a defense or those kind of things where you really need to own your own this thing, right? Own quantum computing hardware, it will probably be all general purpose will move to cloud. Google, IBM, Amazon, etc., etc. Reference document from Isaka, I have no idea. I will let Vanita take that. Can I have your LinkedIn ID? All right. HTTPS. All right, I've replied on the